Hi everybody. I've gone slightly out of order because I deleted my presentation that I made for tonight, but that's right, I've got some here for organic chemistry already. So we'll go through that, skipping ahead a week, I think. Organic chemistry is week 9 or 10. What are you going to do? I'm not very good at admin. What can I say? So organic chemistry is the branch of chemistry that's concerned with carbon-based compounds that are involved in living things. Recently, they changed it to all carbon-based compounds. But I mean, really, it's still mostly the ones that are involved in our living systems. So, carbon forms a massively diverse range of organic compounds. It is the backbone of every organic compound. And each of them have what's called a functional group. So they all have the same backbone, and then they have a functional group that attaches to those, which makes them all different. Can't sit still, even worse than normal today. So, study of carbon-based compounds. As with most things in chemistry, we have just changed it to suit whatever we needed, despite what the original field was about. So, we all have been looking at the periodic table, and I've been drilling it into you each and every week. Where does carbon sit on the periodic table? Don't answer it in the chat, but where does it sit? It sits in group 4. So it has 4 valence electrons available for bonding. Okay. So you can see 4 valence electrons. And all of them are available for bonding. So here's where carbon is special. It can form single, double, or triple bonds with other carbon atoms and other elements. And it gives these carbon-based molecules the diverse range that we currently have. And these carbon chains can effectively be of indefinite length. I mean, I'm sure there is a definite limit to them. And then we have the other elements and compounds that are bonded to it to give it the different functionalities. And this will hopefully make sense. So, whiteboard's coming out early tonight. Why not? There's some organic chemistry that I just did with one of our students. So if we look at every organic compound has this. Got new whiteboard markers, might as well use them. This carbon backbone forms the basis of all of the organic compounds. And what also forms the basis of the organic compounds is when it's attached to hydrogen. So this is the most basic form. This is a hydrocarbon, or a saturated hydrocarbon. And this is the most basic form of an organic compound. Organic chemistry is all about pretty pictures and drawing shapes and writing different names. based on this basic chemical structure. So it can form, each of these carbon can form 1, 2, 3, 4 really strong bonds. So the question that I'd like you to go away and answer is, why can carbon do this? So carbon is in group 4. Silicon is also in group 4. Why can't silicon do this? Now there's a theory that if we didn't have carbon, life would have formed with silicon. But what I'd like you to try and answer is why carbon does, but silicon doesn't do the same thing, despite being in the same group. So we're talking about these strong bonds. So we know, you can see, everyone understand the basis of petrol that you put in your car? Petrol in a car is made up of these hydrocarbons. And whenever we burn something, so if we burn this, we get the energy. So if we combust this in a car engine, we get energy every time for all of these bonds that are broken. So when we burn this in a car engine, those bonds don't exist anymore. We get release of heat energy, and that powers the piston in the car to go up and down. The stronger the bonds that are here, so if this was a double bond, it would have twice as much energy. If we put a triple bond in there, then it has almost 3 times as much energy. So we need to break this bond using energy in order to produce energy. So this is the basis of all of our fossil fuels. So fossil fuels are made up of the dinosaurs and plants, and they are just different variations of this. You'll see 98 octane fuel, 95 octane fuel, 94, 93, 91. And that is just referring to how much energy is in these bonds. The higher the octane rating, the more energy is released. But also it's the more energy is required to be put in. So the more heat is required to break the bonds in the 98 octane fuel. And if you're driving a Toyota Yaris and you put 98 octane fuel in, probably wasting your money. Whereas if you're driving a high performance car that requires a lot of heat, then you'll need to put in 98 octane fuel. Toyota Yaris, not so much. So the simplest one, like I just said, is called a hydrocarbon. It is carbon in the middle, surrounded by hydrogen. Shock horror, I know, very complicated name. And when we start looking at the other organic compounds, They have oxygen attached. They can have nitrogen attached. They can have chlorine, sulfur, bromine, so on and so forth. But they still have that as their backbone, and everything else builds around it. So, we have what's called the functional group of organic compounds. The most simple here, it doesn't have a functional group. Now, a functional group is what makes something else. So this is a fuel called butane. It's in your butane and propane are in your gas bowls. If I were to add simply put an oxygen there, I'm just going to unshare. So if I was to change this, this is butane. This is a fuel that you use to burn your car. I make it OH on the end, it changes it to an alcohol with completely different set of properties. Completely different set of properties. And that's the functional group. When we look at the most simple of the hydrocarbons, where it's just carbon and hydrogen, the fact that they don't have a functional group, and I'll send these slides out after this, the fact they don't have a functional group is their functional group, if that makes sense. So if you look at this slide, you'll see what I was demonstrating there. So ethanol is more commonly known as alcohol. That goes into alcoholic beverages produced by yeast. But the only difference there, as you can see, is one oxygen molecule. And it completely changes it from a fuel that we use in our barbecues to something that impairs judgment and functioning. There's a different kind of, okay, well, I will do it this way actually on the board, as opposed to off the slides. So this is ethane. Don't worry about naming, we'll come to that in a second. This is called ethane. We then change it to this is ethanol. We then have ethanoic acid over this side, and I will explain what this all means. This is ethanoic acid. where it gets a bit weird. This is tetra. Oh, 1, 1, 1. So what do you notice all of these have in common, aside from ridiculous names? Again, don't answer, just if you said that this is the same, you would have been very correct. So, this is a natural gas used in homes. We change this to OH. We make it into an alcohol. We change it to this, the functional group. We get vinegar. Don't worry too much about this one. But if we change the functional group to this, all these molecules, it becomes a gas. If you breathe in, you'll die instantly. Not instantly, but pretty quickly. So they share this. This backbone is the same in all of them. And if you look at them, they all start with E. And we name these organic compounds based partly on how many carbon atoms are in the backbone. Okay, jump on to the next step. This is a set of 3. Now we'll look at the hydrocarbons in a bit more depth. I might do an extra week of organic chemistry. I might do this week and next week as organic chemistry. Or I'll just upload another recording of me talking to myself late at night so that we can see. I'll take this through to the end of this slide. Do an extra week for you. So we have alkanes, alkenes, and alkynes. So if you remember, this was one here was ethane. We then have homologous series. And then we're going to compare the alkanes, alkenes, and alkynes, and I'll teach you the cheater way. Well, not the cheater way, the smart way. So homologous series, as you can see there, they differ by CH2. So what that's basically saying is that the carbon chain gets 1 carbon atom longer. So you can see there, methane is the simplest organic compound. It's just carbon and hydrogen. Ethane is a little bit more complex. Propane, butane, pentane, hexane, getting bigger by CH2 each time. They have increasingly longer chains. So, but each member of the series has a similar pattern, chemical properties, and general formula. So all of these here, except for pentane, are used as fuels when they're burnt for energy. So I'm going to do this on the whiteboard. We have alkanes. This is the very simplest one. And if you see carbon completely surrounded by hydrogen, this is carbon completely surrounded by hydrogen. These lines here are single bonds. So they're sharing one pair of electrons. But you'll also see that there is only one line. Alkenes you'll see a double bond. So this is alkenes. You'll see a double bond or two pairs of electrons shared between the carbon atoms. We then have the alkynes. So we have three bonds between the carbon. Good way to remember, A comes first in the alphabet, one bond. Enes comes second, or E comes second in the alphabet, two bonds. Ines comes third, or Y comes third, three bonds between the carbon atoms. So alkanes, no functional group. No functional group. It is called a saturated hydrocarbon. Alkenes, the functional group is the double bond. Alkynes, the functional group is this. And the functional group is what gives these their different chemical properties. So although they are just hydrogen and carbon, there is this double and triple bond which changes the properties. Just trying to move through this quickly. So we need to name these. I'll share the naming convention. It's not hugely difficult, but the alkanes end with ane. The alkenes end with ene. The alkynes, shokara, they end in ine. So what we need to do is we need to count the carbon atoms on here. So we can see there, meth is 1, eth is 2, prop is 3, bute is 4, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. So this would be ethane, it only has single bonds and there's 2 carbon atoms. This would be ethene. 2 carbon atoms in the chain, and it has double bonds. We go to here and we would have ethine. Triple bonds, so we know triple bonds comes third in the alphabet, so alkyne, and there's 2 carbon atoms, so it's F. So, using that, I'm going to do some examples that you guys can have a look at. So I'm going to share so I'll share the naming convention. So what would this be called? Is it an alkane, an alkene, or an alkyne? Then we need to figure out how many carbon atoms. 1, 2, 3, 5, 6, 7, 8. Once we know that it's only got single bonds, so it will be octane. It has 8 carbon atoms and it only has single bonds. So just going to skip through some of this because we've been through alkenes, alkynes. So this naming convention that we just did works when there's a single chain. Sometimes organic molecules will have their backbone, and then off this one it has so this doesn't, our naming convention before doesn't work because we have this side chain or this chain. So the way that we name these ones instead is we count the longest continuous chain. So that would be 1, 2, 3, 4. So 4, if we look at our if we have our naming convention, it only has single bonds all the way around, so it's an ane. It's got 4 carbon atoms, so it's bute. But then we have this up here, and I'll send out these slides tonight on my list. One second. Okay, so much to do this. This is what we call an alkyl side chain. So alkyl side chain here. So we name this with YL on the end. And then we use the same convention as before. So 1 carbon atom is meth. So this is called butane. And this is called methyl. There's one more step in the process. Now, we have to count the carbon atom that this is coming off. The mistake that most people make is they start left to right, and it doesn't work like that. It's the side, you start from the nearest side to the chain. So this would be 1, when writing in Arabic or Mandarin, and we're going right to left instead of left to right. So the number is number 1. So now we need to stick all of this names together. So we put the number first. So 1, methyl for the side chain, and then butane, because that's the parent chain. So 1 methyl butane. This tells us that there is a 1 carbon side chain coming off the first carbon of a butane backbone. That's what that means. Okay. Another thing that you'll probably never use again once you finish 11, 12 chemistry. You might use it if you go into chemistry at uni, but aside from that, not really. So I'm going to try and get through another set of slides in the next 15 minutes or so. That's 2 weeks worth of chemistry at year 12 level. So I am pushing through this, but I think you guys can handle it. Oh, I opened up the wrong. So we're going to look at the last one in this, and I'm going to do, I've got an organic chemistry SEM video that I'll put to finish this series, so it's a bonus video. So we have these things called isomers. And they are, for lack of a better term, same, but different. So the same molecular formula, so the molecule might have, this is what C2H6, but the 2 molecules don't look the same. There's a difference between this written in a straight line and how the molecule looks in 3D. So then I'll demonstrate that now on the board. So we have a structural isomer, which is same molecular formula, but the arrangement of the atoms in 3D space is different. So we have C4H10. I like to sit down and we can visualize it on here as opposed to me drawing it. So we have butane, C4H10. Same chemical formula, but they are arranged differently. So one is called butane, the other one is called 2-methylpropane. Same formula, different structure. My technical term of same but different. So if, and it's fairly self-explanatory here, if the change is in the chain, then it's called a chain isomer. So instead of having 4 carbons in the backbone, it has 3 carbons in the backbone and a side chain coming off. And this is where it can get a bit complicated. So we have the prefix, which is the number of carbon atoms, whether it's an alkane, alkene, alkyne, or an alkyl side chain gives us the suffix, so on the end of the prefix. And the number refers to the carbon atom in the backbone that the side chains are coming off. So before we looked at a single side chain and a double, and now we have 2. Now it gets slightly more complicated, but it's still the same basic rules. We have, that's supposed to say 5 carbon parent chain, not 2. Here as pentane, we have, so we count from the nearest end. So this end is the closest to the first chain. So it goes 1, 2, 3, 4, 5. We then have a 1 carbon side chain, which we know we call YL. We call that methyl, and it comes off the second carbon. So it's 2-methyl, so same as before. The 2 carbon side chain coming off the third carbon, we call that ethyl. So we then combine them into a singular name. When there's multiple chains, we have to put them in alphabetical order. So we have 3 because this side chain, the ethyl side chain, is coming off the third carbon. We then have 2 for the second carbon, methyl, pentane. Pentane being the name of the backbone. Oh, just hit the wall, sorry. So if the side chains are the same, then we don't list each of them twice. So di, tri. And I'll demonstrate that here. So the same thing here. We name the parent chain first. 1, 2, 3, 4 carbons. It's only got single bonds. So you can see that although it's getting more complex, it's still the same rules as the beginning. 1, 2, 3, 4. So it's butane. Both of the chains are coming off the second carbon. So you have 2 single carbon alkyl side chains. So that's di, as in there's 2 of them. They're both coming off the second carbon. They both only have a single carbon, and the parent chain is butane. Sorry. The other one is a positional isomer. So that means the position of the functional group. In this case, it's a double bond. So it's an ene. The backbone has 1, 2, 3, 4, 5, 6 carbons. So it starts with hex and it ends with ene. And we label where the functional group sits, which is here. So in a positional isomer, so we looked at chain isomers. In this positional isomer, the position of this functional group is the one that varies. So hex 1-ene comes off the first carbon, hex 2-ene comes off the second carbon. Oh, sorry. So we've got through a lot of topics, so I'm not gonna, we don't have time to sit here and answer them all. On my list is to send out some questions for this. I'll put on now. Some basic naming questions. I'll put those, I'll send those in the email with the slides so you can revise everything. So now we get into the what's called the geometric isomers, which is where they are actually in the same order, but their arrangement in space is different. So this stereoisomer, the 2 molecules are connected in the same order, but you can see there's been a rotation of one end or both ends of the molecule, and it's facing this way. But they are still exactly the same formula, but the way that it's arranged in space is ever so slightly different. And there's 2 types of these structural isomers: a cis, where both the hydrogens are on the same side. Then you have the trans isomer, where the hydrogen is on the other side, or the opposite sides to each other.